Good evening, ladies and gentlemen. You are welcome to this session, Cyber Physical Solution for Microgrid. My name is Thanh Quốc Tuấn, professor at CA Liden INES, French National Institute for Solar Energy, and INSTN, Paris-Saclay University. In this section, we have 4 presentations, about 20 minutes for each presentation and 20 minutes for question. First presentation presented by Professor Quốc Tuấn Thanh, CA Liten, Cyber Physical Solution for Microgrid with PV System. Second presentation presented by Dr. Associate Professor Hồng Phương Nguyễn, Eindhoven University of Technology, New Approaches for Coupling with Microgrids. Third presentation presented by Dr. Văn Hòa Nguyễn, G2E Lab, Grenoble, INP, Cloud-based Control for Microgrid. Last presentation presented by Dr. Associate Professor Raphael Kerr, G2E Lab, Grenoble INP, Microgrid Distributed Control, Validation in and Hardware in the Loop environment. Now I will present the first presentation.
Cyber physical solutions to secure and optimize the operation for microgrids with PV system. The integration of the renewable energy or PV system into grid with intermittent sources, low energy, difficult for forecasting. They can have several impacts, such as production and consumption unbalance, stability and protection problem, challenge for managing. However, they have new opportunities. This is why cyber physical solutions are necessary to reduce these impacts, maximize PV integration, maintain a good operation, maximize the PV contribution to ancillary services. Validation by using real-time digital twins are very interesting. For example, this is the contents of my presentation. The integration of intermittent PV system into grid. They can have several impacts on grid, such as voltage variation, demand-supply unbalance, stability and congestion problem, etc. There is also influence of grid operation on PV system, such as voltage variation, voltage surge, protection system. This is why it is necessary to develop cyber physical solution permitting to reduce these impacts, secure and optimize operation. The integration of variable PV to grid, there is a fluctuation of the voltage. Voltage rise in case of strong irradiation and light load. This problem is more severe for weak distribution network. Consequence: risk of blackout, increase aging of inverters, reduce the benefits of PV generation. This is why it is necessary to develop strategies for voltage control. We have developed in auto-adaptive voltage control based on fuzzy logic and local information as presented as here. This proposed solution presents not only technical but also economic advantages. Decision based on local measure, avoiding investment on communication system for DNO. To study the voltage problem caused by photovoltaic system in order to find innovative solution, a low voltage distribution network as here is simulated. This is the variation of the PV production and the daily load curve for residential load and commercial load. Here is the PV production and with the PV, with the PQ classical control, reactive power output are equal to 0. Yeah. And here, the variation of the voltage, there is a over voltage during this period and under voltage during this period. With the proposed solution, all PV inverters participate to control voltage. They can absorb reactive power in order to reduce the overvoltage, and they can provide reactive power in order to increase the voltage. For example, during this period. This is a Q at 9 mode. For this solution, all voltage are maintained in admissible limit. Proposed solution permit to increase PV penetration. This solution is tested by using real-time simulation. From control strategies evaluated by real-time simulation, these strategies are implemented in PV inverters at the Soria for a real demonstration. Without this solution, there was a several disconnection of the PV inverters caused by overvoltage. With the help of the proposed solution, disconnection caused by overvoltage are avoided. Now, I would like to present a coordinated voltage control strategies, CVC, in order to reduce losses, to maintain a good voltage profile, and minimize the reactive power output. With the contrast of voltage of reactive power output and branch current limit contrast. You see here. This is the This is a demonstration of the developed CVC for a real network at Soria in framework of Ethernet project M2M. Communication and control are sent to SCADA system at CEEST about 100 kilometers via gateway using OPC UA. You can see here the grid for demonstration with three inverters. Proposed solutions can be generalized for multi-microgrid. This is the display and graphic interface of the demonstration. System makes it possible to monitor the measured quantities of the Soria networks and send set point to trace PV inverters after optimization by CVC at CEEST here. Now, I would like to present stability, in particularly frequency stability for an Iceland microgrid. In this case, Guadeloupe grid. Here is a Guadeloupe network with a high PV penetration, low inertia, severe stability problem, fast to fall. Scenarios used for this study are 32% of PV penetration, 50% of the PV penetration, 72% of the PV penetration. Fall occurs at t equal to 100 seconds, eliminated 200 milliseconds after. You can see here the variation of frequency, of voltage, and of rotor angle of synchronous generators for 32, 50, and 72% with the proposed solution. By a classical protection based on level protection, the system is unstable. With the solution by using FRT implemented for own PV, the grid is stable. You can see here. Without FRT, the system is unstable. And with FRT, the system is stable here. Now I would like to present this user, the battery energy storage system, BESS, to guarantee the PV power output. You can see here the planned production channel here, PV generation, green curve, and BESS solicitation resulting from optimization here. The management strategies take into account aging costs. Here is a solution for an adaptation of load consumption with the PV production, for example, electrical vehicle charging. The objective is to maximize the use of solar energy to charge electrical vehicle. For this case, without management, solar coverage rate is 55%. And With management, solar coverage rate is 98%. As here, you can see here the power exchange between main grid and EV charging station. With the help of the management strategies, this power exchange is reduced to zero. It is a good self-consumption example. You can see here several demonstrations realized by CA for different management strategies of electrical vehicle charging. I would like to present here a case study of advanced voltage and frequency restoration in an isolated microgrid. The case study is implemented on two remote platforms, Predis here and Pris here, about 70 kilometers. The validation framework was comprised the real-time simulation and physical hardware in the loop platform. This is the Icelandic microgrid. The aim is to maintain the frequency and voltage at reference value and to ensure the proportional power sharing amount BSS. Objective is to investigate the influence of the communication networks on control performance. To examine the behaviors of the control algorithm, voltage and frequency deviation to real device, PV and load at this node is replaced by a real PV emitters and a real electronic load, as here. The profiles of load and PV production in this part is from SCADA, and this part is simulated by OpenRT. There is 3 case tests. First, normal operation. The latency between the two sides of the platform is measured to be consistently about 32 milliseconds. After that, we trigger secondary control remotely. The controllers compensate the deviation and recover frequency and voltage to desired value, is here and here. The controllers was correctly to deal with the disturbance of load, as here, and the fluctuation of the PV production in this moment. Second case, communication with noise. The same at this case, but an additive Gaussian noise is added to communication between the controllers and microgrid. Power sharing amount BSS, the voltage and frequency are then shown in this figure. It demonstrates that the control can withstand communication noise to a certain extent. Third case, under important latency. In this case, we add 500 milliseconds to the latency to investigate the behaviors of controllers in a batch communication. For this case, when the secondary start this void here, the controllers fail to stabilize the microgrid illustrated in this figure here. The overvoltage triggers the protection, the anti-aliasing protection of the PV inverters. Finally, the grid is unstable. The controllers therefore needs to be modified to adapt to the new working condition. This is a microgrid demonstration at the CINS. Conclusion. Cyber physical solutions are very important to secure and optimize the operation of it. Thank you for your attention.
Next presentation presented by Dr. Associated Professor Hồng Phương Nguyễn, Avon University of Technology, New Approach for Coupling of Microgrid. Please.
Everyone, thanks for joining me with this talk related to new approach for coupling of microgrid. My name is Phương Nguyen from Eindhoven University of Technologies, the Netherlands. So today in my talk, I would like to present some of the main topic related to microgrid coupling, including the monitoring capability for grid-connected microgrids, and also the new operation schemes for microgrid so-called fault-initiated islanding. But first, I would like to address a bit the context related to microgrid and coupling aspect. So, as you can see on the slide here, we can see that for the power system, especially from the customer side, we see more and more nowadays the integration of distributed energy resource, including solar PV, wind, electric vehicles, heat pump, and other forms of battery energy storage. Those kind of development allow the customers and local energy communities form a so-called microgrids with a high autonomous operation capability. Of course, then it comes to the question how to coordinate those development of microgrids with the existing distribution grid. What would be the coupling aspect that need to be addressed here in between microgrid and power system? So that's also the big questions currently from our research group related to Digital Power and Energy System Lab, DGPAS Lab. We are currently busy with. So several topic has been listed on this slide as well. So you can see from the left-hand side more related to the microgrid aspects, several topic related to modeling, probabilistic modeling, or by leveraging the data collected with the classification and predictive models we can develop. But also from the system, from the grid side, we are currently also busy with the modeling aspect related to both steady state and dynamic state of the systems, and also to ensure the compliance and interoperability of the microgrid with the distribution grid. We need to also have the testing set up, arranged with proper virtual testing environment, support by digital twin development, for instance. So those are the aspects that we are very much interested in at this moment to address the coupling aspect here between the microgrid and power system. In my talk today, I will more focusing on two specific topics related to monitoring, which is more related to grid-connected microgrid, and islanding, which is the switching between the grid-connected to islanded microgrid operation. So in the first part related to monitoring of grid-connected microgrids, as said earlier, with more and more DIAs and the activities from customer sides, for instance, demand response, demand side management, but also other self-regulated activities from the microgrid perspective. Distribution system operator or DSO, now they need to get to know more insights in what happened in their grid areas. So beside the installation of massive smart meters for the customers, they also have the intentions to install at different levels of voltage in their grid advanced network sensors. So this is a part of the United Grid project, which is one of the Horizon 2020 project we did together with the local startup Smart State Technologies. We deploy the modular smart sensor solution from the companies at different level of the grid, at the transformer with current and voltage sensors, but also to the outgoing feeders with modular smart sensors. Of course, one of the important aspects here is to gather information, ensure the integrity of the data collected from the existing SCADA systems, also with the new developed smart sensors. Data has been arranged within this United Grid project. Besides collecting these data, one of the things we, of course, can think of is to use the data for proper mathematical models developed. And one of the classical models that you may know already, that is by using state estimations to determine network state with the set of critical measurement data. So here is a very let's say, traditional steps that the data is collected and processed before fed into the input data set for state estimations, which is include grid topology and parameters. And measurements is in the form of vector Z, and the error range of the measurement is also play very important role here. And via state estimation, which is nothing but the maximum likelihood estimation process, we can determine the output parameter, which is in the form of vector X state vectors, including the voltage magnitudes and phase angles on the buses connected. This maximum likelihood estimation is expressed via the nonlinear function hx associated with the random error ei, and you know that the errors associated with the measurements are assumed to be the normal distribution. Zero means with the independency among them. So based on that, then the mathematical formulations of the famous weighted least square problem has been formulated to determine the estimation process of the network. So those classical state estimations later has been replaced by the so-called data-driven state estimation, which is also very interesting from the research point of view because of the interesting period of getting more and more data from the grid side. So basically, the whole process of state estimation with weighted least square can be replaced by putting actually the structured neural network into the nonlinear power flow equation here. So basically, it is the work done by one of our colleagues in the lab, Mr. Trần Minh Quân, within the Horizon project FlexiGrid. So in this project, we are looking at the network topologies, structure, the neural network models the same, but also looking at the different layers of the neural network that we have developed to simplify the structures in the way that it keeps the learning process the same. So there's at the end we can obtain the so-called Brunt physics-aware neural network structures that can derive the estimated state of the network in the proper manners. And the work has been tested with the test benchmark 123 nodes employed in MATLAB and OpenDSS with comparable results with the traditional weighted least square methods, as you can see on these tables. But if you are interested, please feel free to get more details from this publication of the work. Besides the state estimation, we also look at the way how to develop the proper models for transformer loading, looking at the geographic, demographic conditions of the similar areas. So basically, here in this work done by one of our researchers, we looked at the living conditions, the geographical conditions, and socio-demographic data collected in the existing areas with the clustering algorithm deployed based on this set of criteria. We can cluster the network areas in one of the rear distribution network in the northern part of the Netherlands into 4 main clusters. So basically, those are the typical clusters in the distribution network there, which we can use as a typical, let's say, load profiles that can be used to via the transfer learning possibility for the new neighborhoods. So the work has been deployed and verified with the simulation models, as you can see here. The results of the 3 existing network and then the new developed network with the estimation, which is showing quite good performance of the estimated value comparing with the measurement. Now, I would like to switch to the next main topics of the talk related to the operation schemes of fault-initiated islanding, which allow a specific microgrid to switch from grid-connected to islanded mode when there is a fault occurs out there in the distribution grid. So you can see also the principle on the right-hand side of the slide. So here in this switching possibility, it is very important to determine the operations of the DER inverters associated with. So the 2 main operation schemes for DERs in this switching sequence is the grid feeding, which is considered as the normal operation of the DERs before fault occurs. And the grid supporting modes is when the the isolated operation mode is activated. But anyways, when the fault occurs, the sequence are as follows. First, with the fault occurs, we switch from pre-fault to fault conditions. And of course, there will be the switch opening, and then the grid fittings landing mode is kick in. And there we have to switch the operation modes of DR to grid supporting ice landing. This, let's say, challenging operation schemes require very strict, rigorous stability analysis to ensure that you are switching from grid connected to island mode in a very stable way. In order to do so, we investigate the root cause of the instability problems when while switching, and came up with a set of, let's say, criteria for stable conditions, including the convergence to the equilibrium states. Equilibrium is within specific limits. There is a need for the local power balance between DRs and the load, and also we have to ensure no unstabilizing or high circulation current between DRs. So some of the typical examples of the operations conditions where switchings are shown on the slides. So you can see that for the stable scenarios, after switchings, you can see the signals is converging to sorry, to one equilibrium state. But if the power balance is an issue, meaning that you don't have sufficient DR capacity in this case, you can see that though the equilibrium state is reached, but the voltage is not recovered at the proper level. And the same happen with the DR circulation current that may increase if PRL design are not properly tuned. So these, of course, very interesting topics, but also challenging, which need to be addressed with proper dynamics to be modeled from device component levels. So here in these studies, our researcher looking at this aspect by zooming and developing the modeling methods to address several challenges. The first challenge related to drop-off behaviors of the power electronic load and DRs, which likely happening when you have the high switching transients between grid-connected and isolated mode of the microgrid. So it is important to come up with the proper models, and in this case we use component-based model to validate the behaviors of the components, not only by having the synthetic models, but also in the comparing with the lab component behaviors. This is very suitable for the time domain transient stability analysis, as also mentioned here. Another challenge is related to the phase unbalance in the microgrid, which is the typical challenge, and in most of the time domain transient stability analysis method, or also Lyapunov-based energy functions stability analysis method, this topic of phase balance has not been covered. So in our work, in our recent work, we propose using copper sequence component models in DQ frame, which can address this challenge properly. And this is one of some of the results showing the behaviors of one three-phase DR grid fitting component. So after addressing the modeling aspect, the task of stability analysis is done. Here, there is a method that we are interested and presented here is the energy function-based TSA. Why is interesting? These methods comparing with time domain TSAs have several advantages, including the capability to analyze all initial conditions instead of only one single initial condition, as can be done by time domain transient stability analysis. And based on that, we can quantify the stability margins, which is defined as the domain of attractions, which is a very interesting concept that can be used for design and planning of a microgrid. But last not least is the capability to reduce the computation burden. So it can enable the transient stability analysis to be online tools for monitoring and controlling the microgrid. So it is just to show some very brief steps for this proposed energy function-based TSAs. So on the left figure, you can see that this is the 2D representations of the state transactions, just to give a kind of impressions, ideas about the methods, which is start with the initial condition x0 via the different stage of for initiated ice landing. You can see the trajectory evolve. The circle with the dot lines represent the domain of abstraction. And of course, you can see for each of the states, the domain of abstraction is developed accordingly. So the middle figure is to present some results of the energy function-based method in DOA1, the blue circles, eclipse, sorry, comparing with the time domain results in green and other method in red. So this is to show that, to confirm that the developed energy function-based TSA is working properly. And in time domain, the behaviors of the microgrid is plotted on the right-hand side figures, which shows also quite stable conditions after flow occurring after flow initiated islanding. Of course, if you are interested in this work, please feel free to read the associated paper here mentioned. So I would like to come to the conclusion about the work so far we have done. Related to coupling of microgrids, certainly it's very important to have smooth orchestrations between the DRs and the existing controllers of the distribution grid. From what we have done so far, we see the important role of getting more and more data and developing the proper data-driven models for enhancing monitoring capability with the better state estimation methods. And the last point related to the new operation scheme for initiated islandings. We see that is a very interesting operation schemes, but it needs a rigorous stability analysis process based on the detailed dynamic modeling and analysis methods like the one proposed energy-based energy function-based change stability analysis. So that's what our findings out of the work, and thanks for your attention so far. If you have any question, please feel free to let us know. Thank you very much.
Thank you, Dr. Phương, for your presentation. The next presentation presented by Dr. Văn Hòa Nguyễn, G2E Lab, Grenoble, INP, Cloud-based control for microgrids. Please.
Good evening, everybody. It's my pleasure to be here with you today on the panel session on cyber-physical solution from microgrid. And for the panel session, I would like to talk about the possibility and potential of using cloud-based control and SCADA as a service from microgrid. I will present the fundamental concept and a case study on using cloud-based deployment of CVC on the critical microgrid in G2E Lab. In general, microgrid control is categorized into three levels. Primary control, secondary control, and territory control. And classical industrial SCADA system and enterprise network are employed for this control and service. And in our research, we would like to explore the possibility of using cloud-based service to deploy various secondary and territory function. And this deployment on cloud might have to improve the availability of our service, and it will enable real-time multi-asset from everywhere. I would like to emphasize the aspect of multi-asset because it's not always the case for classical SCADA system. And another benefit of the deployment on cloud is the scalability and the easy and not expensive upgrading and expanding of the system. And it will also prove a more efficient disaster recovery effort. And finally, moving to the cloud with more with higher performance on computing to have to deploy more sophisticated application, for example, artificial intelligence application or digital twin. And cloud-based SCADA offer many attractive benefits. However, it also introduces some potential risks such as cybersecurity and reliability. And cloud connection rely on bandwidth availability and reliability. So vital information for safety and promotion is particularly important to the operation and functionality of the grid. We can therefore consider the dependency on internet connectivity as a risk and an obstacle toward a reliable cloud-based SCADA. And also, it's necessary to consider that cyber attack might happen to the server or eventually to the data link, which is often out of the internal network. So, from a risk analysis perspective, it's important to consider and to moderate which information to put on the cloud. And finally, we need to consider that the performance of the functions that remain high bandwidth and low latency would be also affected in the cloud-based SCADA. So, depending on the level of data exposure or to the public, a cloud-based SCADA system can be classified as a public, community, or private. So when SCADA applications are entirely deployed on site and run on internet, the system is considered as a private cloud SCADA. And the access to in this case is restricted to local level and might be granted maybe expand it to a certain cooperator to create a community. And cloud computing also offer three service delivery model: software as a service, platform as a service, and infrastructure as a service. They are classified by the level of control the user can access to. Keeping that in mind, we propose several years ago the concept of SCADA as a service, with the fundamental ideas that the advanced SCADA service can be deployed on private or community cloud and interact with a physical grid via the gateway between the operational technology and informatical technology. So due to the reliability and security issue of an electrical grid in terms of response time and availability and so on, critical control and protection tasks should be executed by the local PLC or RDView, and the exchange information should be selected and monitored. And in this approach, the client asset will be done via web service. And this architecture allow firstly the development and deployment of a more sophisticated SCADA service, such as the optimization, artificial intelligence, digital twin, or virtual power plant. But it also allows the integration of third-party SCADA application via API, or the presentation of our SCADA service to a third party. In order to demonstrate the concept of a cloud-based SCADA control and the SCADA as a service approach, we consider a case study of the Smart Grid Interop project. In this project, we aim to creating an interoperability among the 4 experimental microgrid platforms with a common cloud SCADA server. These 4 platforms consist of a wide range of electrical and communication devices and are supervised by 4 different classical SCADA systems. In order to integrate this system to the cloud SCADA server, we developed several OT/AT gateways. The advanced data applications such as forecasting by artificial intelligence, or optimal control and real-time digital twin are deployed on the cloud and are delivered via software as a service. And in this process, the client get access to the system via cloud platform or web service. Particularly, this private cloud has been implemented on for Smart Grid Interop project in the DMZ of our Z3 lab. It provides asset control for each partner by a selection of IP address. And in order to secure the connection, we apply several security measures: encryption, authentication, and provision from a platform side, and encryption, authorization, and authentication from a client side. The server also provides SSL encryption terminal with selective protocol. The requests sent to the server are processed and oriented towards the corresponding service, all in keeping the load balancing. The intermediate gateway only accepts the connection from the cloud server with a specific protocol. So all the critical control and function stay in the local PLC. Only a few selected actions are allowed with a common access from the cloud server. We consider particularly the case of the reduced scale distribution network developed in the Z3 lab. The topology is entirely evolutive and is driven by a SCADA system comprised of several protocols. For example, Modbus, IEC CT1 850, and OPC0. And Ziegler distribution grid consists of 17 line and 14 node and can be reconfigured in real time. The project has been chosen to demonstrate the capacity of our cloud architecture to improve classical control, generally driven by SCADA. For this case study, a centralized CVC control has been implemented. So the CVC is deployed on on the cloud SCADA server and interact with the platform via the OT IP gateway. In general, it's executed every 3 minutes. For each circle, the CVC algorithm gets the measurement from the SCADA system and the user configuration. For example, the executing mode, the bus function, and the way of in the objective function to formulate the power flow problem and the optimization problem. It then optimize the problem to calculate the P and Q set point of the generator using a third-party solver. The set point are then sent to the static interoperable interface for visualization and to the automat for applying the control. The objective function in of the optimal coordinated quality control algorithm envelope 3 criteria: minimizing the power loss, minimizing the voltage deviation, and minimizing the reactive power injection to the grid by the renewable energy resources. So we have here the web interface of the CVC in which we can choose between a suppression mode where the algorithm only suppress the set point and the user can choose whether or not to apply them manually, and auto control mode where the algorithm will apply the output set point directly to the PLC. And from this interface, we can also change the way of the 3 criteria in real time. So I would like to invite you to watch a demonstration of the platform's integration to the hybrid cloud server and the implementation of the CVC. So in order to evaluate the performance of the CVC via cloud via SCADA service, we consider several KPI. Mainly the temporal mean of the reduction in terms of power loss, in terms of voltage deviation, and in terms of reactive power injection, and their value in percentage with respect to the value where no control will apply. And finally, to quantify the CVC benefit over the daily profile, the gain in energy consumption, reduction in energy loss is calculated as delta E. So in our base study, we use the real profile from our real PV installation, and we reduce the scale from 1 day to 1 hour to facilitate the test. And we run the test with 3 different settings. In the first setting, we put a lot of weight in on the first criteria on minimizing power loss, and less weight we consider for V and Q for the voltage deviation and reactive power injection. So the delta N can reach 50%, and the daily energy gain can reach 23 kilowatts. In setting 2, we put a lot of weight on the voltage deviation criteria, and as you can see, it had been the delta V had already been increased up to 32%, and however, it comes with a compromise of the delta N and delta E. In setting 3, we consider a lot of weight on delta Q, on the reactive power injection, and less weight on delta V and delta N. So in this case, we despite the fact that we increase a little bit of delta Q, we can see a reduction in terms of delta N and delta V, as the daily energy gain is the lowest of the 3 criteria of the 3 settings. So in general, the CVC work correctly as expected. It shows significant gain in all the 3 considered criteria, and it improves the performance of the grid in terms of efficiency. It means less power loss and power quality. It means less voltage deviation and reactive power injection. So, and when we adjust the weight of on the different settings, the optimization process work accordingly. Particularly, we obtain the most gain in delta N in setting 1, where the priority were given on power loss, and in setting 2, we obtain the big gain in delta V with our optimization process. This priority on voltage deviation. The only exception is in setting 3, where we do not achieve a lot of increase in terms of delta Q. Actually, delta Q were very similar in all the 3 cases. In my opinion, it may relate to the fact that reactive power from the renewable energy were required to for the regulation of voltage control, and to keep the voltage to satisfy the in order to satisfy the voltage constraint. So that's why we were not able to reduce a lot in terms of delta Q. However, 60% improvement with respect to the case with our CVC is already considerable. In general, the CVC algorithms allows the grid operator to avoid the loss from 16 to 23 kilowatts per day as a function of the configuration. So in conclusion, the proposed cloud architecture offers great possibility, and maybe the enabler for various advanced secondary and tertiary control of microgrid. And we have also demonstrated the feasibility of the approach via a case study of coordinated voltage control on a real grid. certainly, city and subject and electrical grid is also a critical system. So we will need further research on, especially in terms of the influence of moving to the cloud, to the performance of the grid and the cybersecurity aspect. Thank you for the attention, and if you have any question, it will be my pleasure to answer.
Thank you so much for your presentation. And the last presentation presented by Dr. Associate Professor Raphael Kerr, G2E Lab, Grenoble INP, microgrid distributed control validation in and hardware in the loop environment.
Good afternoon, ladies and gentlemen. That's my pleasure to present you today control prototyping and power hardware in the loop for microgrid assessment, a work that has been done in Grenoble INP, in Université Grenoble Alpes, by some colleagues of mine. So I'm Associate Professor Raphael Kerr, and I'm presenting it on behalf of Catalin Gavriluta, that was a postdoc, and Lam Nguyen, that was my PhD student. So let's start with corporate presentation. Grenoble INP is the Institute of Engineering and Management of University Grenoble Alpes, and the G2E lab, which is my lab, is the electrical engineering laboratory. And this lab is hosting one of the largest academic teams on power system in Europe. Indeed, we are training and hosting more than 30 PhD students. Part of what I will present to you today was supported by the French Research Agency, and we had a project about optimal control of small base station. And in fact, everything was about how to distribute the intelligence and the control of a smart grid with the support of ICT network, and more especially the wireless cellular network. So we are starting from a centralized viewpoint with a very large power system feeding the transmission system and which is feeding the distribution network, to something that is much more distributed, with distributed energy resources in the grid, producing, storing, consuming energy. And part of these distributed energy resources can be the supply of the cellular network or ICT network that will by itself be allowed to support or to give some services to the grid. So maybe you ask yourself the question, why a mobile network? In fact, it's very important to keep in mind that the mobile traffic is exploding. I mean, we are having more and more communication in the grid. So from voice to data, the traffic growth is rocketing, and the cost itself is increasing, of course, following the data. The revenue is not that large, and in fact, for all the telecommunication company, it's important to reduce CO2 emissions, showing that they have some sustainable viewpoint about the society and their industry. So that's why many telecom operators are investing in solar-based stations. Then we can claim that, in fact, everything was about how to optimize together wireless cellular network and its control with the power grid that was feeding it. At the end, we really want to create a cyber-physical framework for real-time distributed control and optimization in smart grids. Let's speak about practical objectives. So we want to validate distributed control. So that's why we did propose a platform for testing distributed application in the electrical grid. It was built about real-time simulator, OpenRT, but not only RTDS as well. That is a tool extensively used in the power engineering world. And we wanted to have, aside from those real-time simulator, a platform that would be low cost and developed using open source resources. It allows to test the interaction between ICT and power systems. Of course, a side theoretical objective related to the different algorithm for distributed operation we wanted to test or to set up. The principle is very clear and clean. We have a model of the physical system running on a real-time simulation, and thanks to a homemade built-in asynchronous communication block, we're able to send information to a data server, and this data server will support the communication to a multi-agent system. Getting, of course, agents are able to communicate together, but they're able as well to send back information to the real-time simulator, so to have at the end a real-time simulation with devices tested that are outside, and this is completely a control hardware in the loop testing. To be more clear and specific, in fact, we are having Raspberry Pi that are hosting code in Python. We are using the Google implementation of the remote procedure call, RPC, allowing a client-server communication between the Raspberry, each of them hosting a server, but as well client, to multiple neighbors. The Raspberry hosts as well a distributed algorithm, such as ADMM or consensus algorithm. On the left-hand side, we can see at the end, we are having several possibilities to exchange communication. So either with wire, or we can use, thanks to the release of the Raspberry, Wi-Fi communication. Let's start with the first test case among the three I want to present today. It's a distributed optimal power flow that is for multi-terminal DC grids. This work has been carried in Grenoble by Katalin Gavriluta, and you can find some references if you want to have more information. So, aside from building the cyber-physical system that was able to test and validate this distributed control hardware in the loop, Katalin was building a simulation in OpalRT and was developing by himself ADMM algorithm with, you will see, we did test two different layers to communicate. So with the fastest one, 12 millisecond inter-agent communication delay. And with this complete MTDC network, with less than 300 iterations and less than 60 seconds, he was able to find a solution that was identical to a centralized implementation. So we can see on the right-hand side the convergence of the different computation that was able to be implemented in the real world after the 60 seconds I was telling you. And so to get the same result that you would have with a centralized optimization. To briefly describe the results we got, in fact, and to prove the added value of the framework we did develop, what is of interest is being able to assess the various performances depending on different external factors. For instance, as you can see here, you are having some different performances depending on what type of communication you're using. So either it is wire-based communication, or if it is using the Wi-Fi internal to the Raspberry Pi. You're able as well to see the difference of, let's say, computation time per agent, so to see which one are with the most heavy communication process, so to, for instance, optimize them, put them more computation power, or to see if it's possible to distribute even more the computation. Second test case I want to present you is secondary control scheme, or frequency restoration reserve, that was implemented by LAM a little bit later, playing this time with AC microgrid. And so I'm presenting you an agent-based distributed control using finite time consensus algorithm with a nonlinear law that is presented in the PhD that you can find a reference in the bottom part of the slide. On the right hand side, you can see the test case we are using. So just for this example, it's a 4-node network, including 4 energy storage plus 3 loads. So as you can see in the slide, in fact, the device layer, everything that is related to the modeling of the component and the let's say control that is below the millisecond, is implemented in OpalRT. So both device layer and control layer are included in OpalRT, and the different algorithms that are converging toward the correct frequency, so to restore the frequency, is implemented in an agent way of thinking inside some Raspberry Pi that are communicating together, so to be able to coordinate themselves and to reach common objectives. Let's keep in mind that we are doing what we call control hardware in the loop. So that means that there is a real-time simulator that is at the same time simulating the behavior of the differential equations of the devices you put inside your model, but is including as well a low-level control, for instance, droop control, and everything that is here is completely inside the real-time simulation. But then outside, you have the set of agents that are willing to have some different objectives. At first, trying to share the power and share the state of charge. They are willing to restore the frequency, and they are willing to restore the voltage. The test case is the following. At the beginning of the simulation, the state of charge are different. So then the consensus algorithm will, by modifying the output power of the energy storage, will get back in less than 70 seconds back to the same state of charge. And then the load 2 is going on. And in less than 20 seconds, in fact, your set of power are converging and are back to a new value that is the one of the distributed control. A few seconds later, we are turning off the load number 1, and of course you can see that everything is going back to a very good behavior, and the set of powers we are having from the different energy storage is as good as, in fact, we are keeping, as I was explaining before, we are keeping the same state of charge while still keeping the voltage and the frequency in the correct magnitude order we want to have. Thanks to those results, we wanted to extend even more the process, and that's why we went to a control power hardware in the loop simulation. So we took this specific example, so a very small microgrid that is a load fed by some energy storage units that are distributed, taking into consideration the network. And in fact, the idea is to run the simulation of the hardware and the software thanks to real-time simulation, interacting with some power amplifier with real energy storage, while having the control of the 5 energy storage units distributed into 5 Raspberry Pi. So let's present one of the power hardware in the loop results. And the first scenario I want to present you is about a decrease of the load from 36 to 25 kilowatts. And what you can see here, of course, obviously, when the load will be decreased, the frequency will increase. And as this is a step-by-step scenario and a consensus algorithm in which you need to have the value to react, then you need to wait the next end of computation and consensus, so to implement modification of the various power in the grid. And what we want to present here is the frequency restoration step. And so, as you can see here, slowly by slowly, thanks to the control of the energy storage unit, that is a real one, plus the 4 others that are simulated, you have the frequency that is going back steadily to the correct value. Second scenario I can present is to try to demonstrate the strength of distributed control and typically plug-and-play features. Plug-and-play means that I can modify my system and the optimization will still work correctly, which is something that you cannot achieve with central controller that is very deterministic. So what we did here, we just disconnect one of the energy storage units and we saw the behavior of the system. So that's what we can see here. After a few seconds, you lose one of the energy storage that was producing, so there is a frequency drop. And after a few steps, of course, the consensus algorithm will drive the system and will take back the frequency to the nominal value. Let's now jump to the third and last test case, that is a distributed optimal power flow, this time on AC microgrids, still done with ADMM control. This test case is related to a microgrid, that is a 6-node microgrid, including 1, 2, 3 loads and 1, 2 energy storage units. And the idea is that those storage units will discuss together with the different agents at different locations, so that the other agents are sending information about the voltage values, among others. And the idea is that we are optimizing the setting of the energy storage system, both on active and reactive power, to achieve some objectives. Implementation is still the same. The 2 energy storage units are able to communicate with their neighbors thanks to a client-server RPC interface. And the idea is that thanks to the values they are getting, we are able to run an alternative direction of multiplier that is fully distributed optimal power flow. Once you get the set point, of course, you're able to give the value to the local controller and completely jump in this control hardware in the loop validation. As you can see here, we have been playing with the raw value that is very important in the ADMM, that is supporting the modification of the Lagrange multiplier and the ability to converge quicker or faster. Of course, if you are willing to go too quick, you might get some oscillation. So at first, compared to a centralized optimization, we were drawing the reaction of the different agents communicating together and slowly by slowly going toward the same value as you can get with a centralized optimization, but still with different performances depending on the value of rho you are selecting. To see the real-time reaction, we created a scenario in which the value of the load was modified, in fact, at T2 and T4, so having 3 different values over the time. We can see, as a result, that the consensus algorithm is very quickly reaching a new target, a new value, that is optimizing the different value we want to optimize. Here it was the power losses. And in fact, after the loop of 60 seconds we selected, in fact, the implementation is done on the devices. And then there is a modification of power of the load. So after the loop is able to get the new value, there is a convergency that is done and that is implemented a little bit further. And the same with the evolution of the load at T4, then T5 will be the time where the ADMM will finalize the convergency and will give the new setting. So what you can see here is that we did select, thanks to the previous analysis, parametric analysis, we did select a raw value of 25. And you can see that with much less than 1000 iteration, the ADMM processus is very quickly getting to the same value as you would get if you have a centralized optimal power flow. So let me conclude quickly about this presentation. So prototyping microgrid is a key to decrease cost and ensure both good behavior and high quality of supply. Control mechanism is crucial, and distributed control is allowing a better flexibility and is avoiding this common point of failure that is the central microgrid controller. They nevertheless need ICT infrastructure with a rigorous sizing on the service level objectives. And the presented infrastructure is allowing the test in advance to validate the efficient control of your microgrid. Thanks a lot for your attention, and we'll be able to answer to the questions a little bit further.
Thank you so much for your presentation, and thank you so much for your participation in this section. And now, the question, please.